Hi everybody. Today what we're going to talk about is a bit more detail about free energy. We've brought up free energy in a couple of different contexts, and what we want to try to do in this video is add some more detail to free energy, and we're going to begin to develop the connection between this thing we've been calling free energy and the concept of equilibrium in a little bit more of a quantitative way. So let me get my title out of the way, and let's just talk a little bit about the ideas that we already have in place when it comes to free energy. So for example, when we first saw free energy, we saw it in the context of entropy. If you'll recall, we introduced delta G as being equal to negative T times the delta S of the universe. All right, that's when we first introduced it. Free energy change is really about, in this context, what's going on with the entropy of the universe at a particular temperature. And this allowed us to talk about spontaneity. If the delta G is negative, that means that the entropy of the universe was going up, and so the particular process you're looking at must have been spontaneous. We've also talked about how delta G is going to be equal to 0 if you are at equilibrium. Now, we haven't played around with this idea too much, and we're going to begin to get to that towards the end of this video, but this is kind of the thermodynamic definition of equilibrium. Now, you can kind of see a connection between these first two equations. If the system is at equilibrium, delta G is equal to 0, well then the delta G up here is also equal to 0, which must mean that the delta S of the universe is equal to 0. So a system that's at equilibrium is having no effect on the universe. That kind of makes sense because an equilibrium system doesn't involve any net change. Now, another idea we've been sort of hinting at when it comes to free energy is the difference between delta G and delta G with a little superscript 0 on it. Now, we haven't gone into too much detail as to what the difference between these two concepts might be, but I'll introduce it here. Essentially, the idea is that delta G without the little superscript is the free energy change for a process without regard to specific conditions. Delta G with the little superscript 0, that refers to standard state conditions, being 25 degrees Celsius and 1 atm. Most of the time when we use the numbers in the back of the book in the appendix, or we might use Hess's law, we're typically finding delta G 0 values. But not all of our chemistry happens at standard conditions. Not all of our chemistry happens at 1 atm and 25 degrees Celsius. So what we really need to be able to do is find the delta G for any condition we might have conceivable in the laboratory setting. That's what this video is going to focus on. Now I'm going to go ahead and get rid of my face for now because we want to save a little bit of space. And what we're going to look at are some PowerPoint slides that I've already made up in advance to walk us through. So let's start with the what I like to call the most important equation ever, this guy here, delta G equals delta H minus T delta S. All right, if you want to evaluate spontaneity, you need to know the enthalpy and you need to know the entropy changes. And we're, of course, limiting ourselves to a specific temperature, a constant temperature. Now, maybe you recall, but enthalpy change is heat exchange at constant pressure, so there's no pressure dependency there. But as we saw with some of the ideal gas equations associated with entropy change, if you mess with the pressure, you're going to mess with the entropy. So while H may not depend on pressure, S does, and therefore free energy change is going to depend on pressure. Now I'm going to show you this next equation, this guy right here, and I'm just going to introduce it without derivation. The derivation gets a little bit involved, but I can kind of walk you through it so that it makes some sense. What this equation is setting up is that the free energy change is equal at any condition, notice the lack of the superscript there, is going to be equal to the free energy at a specific condition, namely thermodynamic standard state, plus what I like to refer to as a correction factor. That second term in this equation allows us to manipulate temperature and allows us to manipulate the pressure. So the free energy of a material is equal to the free energy at standard conditions plus the free energy at which we find that material exactly existing. So what we're going to do is we're going to use this second equation here, G equals G0 plus RT ln P. we're going to go ahead and develop a more general change of free energy equation that we can use for any conditions, not just standard conditions. I'm going to kind of walk you through sort of a cheesy little derivation here, and we're going to use a specific example. Okay, our specific example is going to be this guy here, nitrogen reacting with hydrogen to form ammonia. This is a pretty important reaction in the industrialized world. It makes ammonia, and we need ammonia to make all the fertilizer. And if we didn't have all that fertilizer, we wouldn't be able to feed the population of the world very well. All right, so the free energy change of this whole reaction here is shown here. The delta G of the reaction. How does free energy change when we go from reactants to products? Is going to be equal to twice the free energy of ammonia minus the free energy of nitrogen minus the free energy of 3 times hydrogen. So this equation here is our standard products minus reactants type analysis for a free energy change. So what I'm going to do is I'm going to plug in for each of these G values in our products minus reactants the G equation that I showed on the previous slide as it applies to each specific ingredient in our reaction system. So the G of ammonia under any condition is equal to the G of ammonia under standard state conditions plus a correction factor that's correlated to the pressure of ammonia. We've got the same equations for nitrogen and hydrogen. So hopefully you can see where I'm going to be headed with this algebraically. I'm going to take these 3 expressions here and I'm going to plug them into my products minus reactants calculation there on this next slide here. So then the delta G is equal to twice the G of ammonia minus the G for nitrogen minus 3 times the G for hydrogen with these specific non-standard state G substitutions plugged in. Now this is looking kind of busy up here, so I'm going to start to collect similar terms. So I can pull out the G zeros from each of these parenthetical statements there. And then I also have an RT factor, as you can see, next to each of my natural log pressures. So I can pull RT out and have a parenthetical collection of the natural logs of my pressures. And then I'm going to take advantage of a property of logs that I suspect all of you folks know about. Namely, if you have x ln y, that is equal to ln y to the x. So I'm doing that with 2 ln p of ammonia, so it becomes ln p squared of ammonia. Do that with negative ln pn2, becomes the natural log of 1 over the pressure of nitrogen, and negative 3 ln pH2 becomes the natural log of 1 over p cubed. So now I'm going to take these revised natural log expressions and I'm going to plug them into there, just to do a little bit of quick substitution. And this is going to start developing something that you're going to recognize. Believe it, we are just rearranging the variables here, right? So my delta G0 comes from this guy here. So here's what we get. We now have the delta G under any condition is equal to the delta G zeros that I have from the previous slide, plus that RT factor that I pulled out, times the natural log of the pressure of NH3 squared over the pressure of N2 and the pressure of H2 cubed. So that's my delta G0 term there. I've collected the RTs there and my pressures in that in the brackets there. So now what this big hairy scary thing looks like for this specific ammonia reaction is what I have here in the box. And this is a pretty important equation. We've got it boxed. Let's go ahead and star it, and I think we ought to smiley face it as well because it is that important. What we have here is essentially the free energy change for a reaction under any condition is equal to the free energy change associated with standard state conditions plus RT times the natural log of Q. Do you remember Q from sophomore year? This is the reaction quotient. It's the mass action expression, the products over reactants, raised to the power of their balancing coefficients. It's like the equilibrium constant, K, capital K, but you're not yet at the equilibrium condition, right? So if you have your system and it's getting towards equilibrium, then you can evaluate its current status. That's the reaction quotient, Q. All right, now we have talked already about a few different ways to calculate delta G0. We've got products minus reactants. We might have to use a Hess's law analysis to combine some reactions to get the delta G for our target equation, but we do have a few different ways of getting delta G zero. Now I can figure out the free energy change associated with a reaction even if I'm not specifically at 25 degrees in 1 atm. Or to put it more accurately, even if my materials in the reaction are not in the phase that they would be at if they were at 25 degrees in 1 atm. So there's some subtlety to the difference between delta G and delta G zero, and we're going to keep elaborating on that as we go through this unit. So what I'd like to end with is a practice problem. So here we've got carbon monoxide reacting with hydrogen gas to make methanol. What I'd like you to be able to do, what I'd like you to be able to come into class with is your attempt to solve this problem. I want you to find the non-standard free energy change for the reaction up here, assuming that you're at 25 degrees, so I'm not going to mess with the temperature, but I am going to mess with the pressures. If we were at standard pressure, CO and H2 would be 1 atm. But as you can see here, they're 5 and 3 atm respectively. So go ahead and first calculate delta G zero, given the information I've shown you, and then calculate delta G given these specific pressures. And see if you can come in with your answer into class when we meet. And we're going to talk about some of the important distinctions between the values you have for delta G zero and the value you've just calculated, hopefully, for non-standard free energy change for delta G without the superscript. That's all for now. We'll see you in class.